Welcome to the Auxiliary Power Unit lesson in the PMDG 737 Next Generation Groundwork from Angle of Attack. This lesson will cover the following topics. We'll start with an overview of the Auxiliary Power Unit and its primary components. We'll move on to fuel supply, start sequence, operational modes, altitude operational limits, shutdown, automatic load shedding, and a lesson summary. The Auxiliary Power Unit, or APU, is a gas turbine engine capable of providing electrical and pneumatic services on the ground and in the air. It allows the aircraft to be self-sufficient on the ground without the need for ground power. The 737 Next Generation uses the Allied Signal, now Honeywell, 131-9B APU. The 131-9B is able to start and operate up to the aircraft's maximum certified altitude of 41,000 feet. The APU is installed within a fireproof compartment in the tail of the aircraft. A firewall isolates the APU compartment from the aircraft fuselage and the horizontal stabilizer assembly. The APU inlet door is located on the right side of the aft fuselage and is automatically controlled. This is a NACA type inlet, a concept originally developed by the US National Advisory Committee for Aeronautics in 1945. It is a low-drag inlet designed to allow air to flow into the duct in flight. There is an inlet flow deflector that modifies the airflow into the intake to ensure that it is laminar and appropriate for ingestion into the APU. After combustion, the APU exhausts gases through a muffler and then out of the tail cone. The high-speed flow of the APU exhaust forms a low-pressure area inside the APU compartment, which pulls outside air in through a second hole in the tail cone. This is called the adductor inlet, and draws outside air into the APU compartment, cooling the APU oil. This is an efficient means of cooling and removes the need for a separate cooling fan, eliminating another moving part. An electronic control unit, or ECU, continually monitors and controls the APU from start to shutdown. It also provides shutdown protection in the event that any one of several parameters goes out of limits. We will be discussing shutdown protection later in the lesson. The APU is very different to the two CFM56 engines on the 737. It has three primary engine components: the power section, the load compressor, and the accessory gearbox. The power section drives the load compressor and the accessory gearbox. The power section consists of a single-stage centrifugal compressor, a combustion chamber, and a two-stage axial flow turbine. Air enters the APU through the air inlet and is directed into the centrifugal compressor, which throws it outwards, compressing it. The compressed air is then directed into the combustion chamber, where it is mixed with fuel and ignited. Ignition and expansion of the gas in the combustion chamber forces it through the turbines, spinning them. The turbines are connected to a single shaft, which in turn is connected to the centrifugal compressor. Also attached to this same shaft are a starter generator, gearbox, and the pneumatic load compressor. The purpose of the pneumatic load compressor is to supply bleed air to aircraft systems that require it, such as air conditioning, pressurization, ice protection, and for engine start. The key difference here is that the two main engines supply bleed air from the power section, while the APU has a dedicated compressor for the job. Because the pneumatic load compressor is attached to the same shaft as the engine compressor, they both spin at the same RPM. In order to vary the amount of bleed air taken from the APU, the ECU opens and closes inlet guide vanes in the load compressor inlet. These control the amount of air that enters the load compressor, and consequently the amount of air taken from the APU for aircraft systems. The inlet guide vanes move from 15 degrees to 110 degrees as bleed air demand changes. We will be furthering our discussion here about how the ECU uses the inlet guide vanes later in the lesson. The accessory gearbox is also connected to the APU shaft. The accessory gearbox reduces the high rotational speed of the shaft to a lower speed for the accessories mounted on the gearbox. The gearbox turns the APU starter generator and other components. The starter generator is used when starting the APU and generates electrical power once it is running. We will cover the starter generator in more detail later in the lesson. Fuel supply to the APU is controlled by the APU fuel control unit. The fuel control unit regulates the fuel supply for different running conditions and uses a motor driven by the accessory gearbox. The APU uses the same fuel supply as the two main engines, and fuel piping is arranged such that the APU normally takes fuel from the left side of the fuel system. The APU is capable of drawing fuel without positive pressure from the fuel pumps. When no fuel pumps are operational, fuel is suction fed from the main tank number 1 using the fuel control unit's own motor. Operating without the assistance of a fuel pump can reduce the service life of the fuel control unit motor, however. To address this, an automatically operated DC fuel boost pump can be installed as a customer option. This pump draws fuel from main tank number 1 when the APU fuel control unit senses low fuel pressure. This provides positive pressure and preserves the service life of the fuel control unit. The DC fuel boost pump is usually used during APU startup when no AC power source is available to power the AC pumps. Under normal conditions, once the APU is running, an APU fuel pump is used to pressurize the system. There are 2 AC pumps in each tank. The fuel system features a crossfeed valve that effectively isolates each side of the fuel system from the other. With the crossfeed valve closed, any of the 3 AC pumps on the left side of the system can supply the APU. This includes the 2 main tank number 1 pumps and the left center tank pump. The main tank 1 aft fuel pump is normally used to feed the APU on the ground. If the APU will be run for an extended period, the left center tank pump may be used to prevent a fuel imbalance. With the crossfeed valve open, fuel may also be fed from main tank number 2. Operation of the DC fuel boost pump is automatic, but the AC pumps must be manually selected on or off on the forward overhead panel. When an AC pump is used and pressurizes the system, the DC pump automatically shuts off. APU fuel consumption is roughly 225 pounds per hour running both packs. This is very much a ballpark figure, as fuel consumption varies depending on electrical load, altitude, and a host of environmental conditions. APU start is controlled by the ECU, which stands for Electronic Control Unit. It is a fully automatic start sequence. The battery switch on the forward overhead panel must be set on before the APU can be started. The APU fire switch on the aft electronics panel must also be in, and the APU fire control handle in the main landing gear wheel well must be in the up position. Controls and indications for the APU are located on the forward overhead panel. The start sequence is commenced by holding the APU switch momentarily to start. The switch is spring-loaded back to the on position and will return there once released. When the switch is selected to start, the electronic control unit opens the APU fuel shutoff valve and the APU inlet door. Either 28-volt DC power from the battery or 115-volt AC power from AC transfer bus number 1 may be used to start the APU. This passes through the start power unit, which converts it to 270-volt DC power. The start power unit then forwards this to the start converter unit, which converts it to AC power for the starter generator on the APU gearbox. As the name implies, the starter generator performs 2 main functions. It supplies the initial rotation of the APU during the start cycle, and provides a source of electrical power for aircraft systems once the APU is running. If starting on the battery, there will be a significant amperage draw indicated on the AC and DC metering panel when the starter generator kicks in. This is usually in the region of a 400 amp draw. It takes a lot of power to get the APU turning. Additionally to the negative amps indication, the battery discharge light will illuminate. The APU draws power from the main battery for startup, so the auxiliary battery is automatically isolated during APU start. The low oil pressure light will illuminate during the start process, and will extinguish once the APU oil pressure reaches normal levels. The APU's exhaust gas temperature indication may fluctuate throughout its entire range during start, prior to normal EGT rise. This is normal and has no adverse effect on starting the APU. Note that there are no limitation indications on the EGT gauge. EGT is monitored automatically by the ECU, and the APU will be shut down automatically if it exceeds limits. It is therefore not necessary to monitor EGT during APU start. The ECU commands ignition and fuel injection during startup automatically as the APU reaches the appropriate speeds. The start cycle will terminate automatically after 120 seconds if the APU has not yet reached the required RPM to disengage the starter. The start cycle may therefore take as long as 120 seconds, and the APU should be run for a further minute after start before it is used as a bleed air source. This minute of idle running is intended as a stabilization period to extend the service life of the APU. Although the start cycle itself takes a minute or so, if powered from the battery at this point, it uses the equivalent of approximately 7 minutes of battery life. Once the start cycle is complete, and the APU has reached 95% speed, the ECU gives a ready-to-load signal to other aircraft systems. This signals that the APU is ready to accept pneumatic and electrical loads. The electrical system indicates this to the flight crew by way of the APU Gen Off bus light, which illuminates blue when the APU is capable of powering an AC bus but is not yet doing so. There is no direct equivalent indication for the air system. APU operational modes. We have already stated that the APU should be run for at least 1 minute after start before it is used as a bleed source. Taking bleed air from the APU places a considerable load on it, far more demanding than taking electrical power from the starter generator. We gave a brief overview of the inlet guide vanes earlier in the lesson and explained how they allow the ECU to control the amount of bleed air coming from the APU. The ECU selects from 4 bleed air modes depending on demand from aircraft systems: no bleed mode, duct pressurization mode, main engine start mode, and air conditioning system mode. The no bleed mode is set when there is no bleed air demand from the pneumatic system and the APU bleed air valve is closed. When the pilot selects the APU bleed air switch off on the forward overhead panel, the APU bleed air valve closes. The ECU closes the inlet guide vanes to the 15-degree position. Bear in mind that even without any bleed air demand, the load compressor will still be spinning as it is attached to the shaft along with the APU power section components. To keep the load compressor cool, the inlet guide vanes do not close fully, even in no bleed mode with no bleed air demand. They close only as far as 15 degrees as discussed previously. The ECU sets duct pressurization mode when the APU bleed air valve is open, but there is no actual demand from the air system. In this case, the inlet guide vanes open further to allow the load compressor to pressurize the pneumatic system air ducts. Main engine start mode opens the inlet guide vanes as needed to meet the high airflow requirement of main engine start. Air conditioning system, or ACS mode, sets the inlet guide vane position as necessary to supply bleed air to the air conditioning system. The air conditioning system itself has 4 modes of operation: 1 pack in flight, 1 pack ground, 2 packs normal, and 2 packs high. The ECU opens the inlet guide vanes to the appropriate position for each of these modes so as to supply the required airflow. We won't go into detail on the ACS modes now, as we include a comprehensive discussion of these during the air conditioning lesson. It is, however, important to highlight the effects on the APU of single and 2-pack operations. APU fuel consumption is considerably greater when operating a single pack than when operating both. This might sound counterintuitive, but we'll explain why it's the case. A single pack must work much harder than 2 packs to cool the cabin to a given temperature. The APU must therefore supply higher pressure bleed air to allow the single pack to function. To supply higher pressure bleed air, the APU inlet guide vanes must open further than they would otherwise have to supply both packs. The further open the inlet guide vanes are, the greater the torque required to keep the APU rotating at a constant speed. This requires the fuel control unit to inject more fuel, increasing fuel consumption. Additionally, although a single pack requires greater pressure than 2 packs would, it requires less actual quantity of airflow. There is therefore a considerable excess of bleed air produced that is not required. This excess bleed air is exhausted through a surge control valve, which ducts it through the APU exhaust. This increases exhaust gas temperatures, and the additional airflow through the exhaust can increase the noise signature of the APU by approximately 2 decibels. Running on both packs on the ground therefore reduces noise, reduces fuel consumption, and extends the life of the APU hot section. This is the recommended practice. The APU is able to start and operate up to the aircraft's maximum certified altitude of 41,000 feet. There are limitations on the services it can provide, however, both electrical and pneumatic, that vary with altitude. The APU can provide 90 kV-amp electrical power up to 32,000 feet. Above 32,000 feet, only 66 kV-amp electrical power is assured. The APU can provide 66 kV-amp electrical power up to 41,000 feet. The APU can provide both electrical and pneumatic power simultaneously up to 10,000 feet. Pneumatic power alone is available up to 17,000 feet. These operational limits are a result of reducing air density with altitude. The higher the altitude, the less oxygen per unit volume there is for combustion by the APU. This limits its performance, and thus its ability to handle pneumatic and electrical loads. Like the start process, the electronic control unit, or ECU, controls the shutdown automatically. There are 2 types of APU shutdowns, a normal shutdown and a protective shutdown. The normal shutdown is initiated by placing the APU switch to the off position. This signals the ECU to begin the shutdown process. The normal shutdown is preceded by a 60-second cooldown period, which begins as soon as the APU switch is selected off. When the APU switch is selected off, the ECU performs several actions. It removes the ready-to-load signal, thus indicating to aircraft systems that the APU is no longer ready to accept pneumatic or electrical load. It closes the APU bleed air valve, closes the inlet guide vanes to 15 degrees, opens the surge control valve, de-energizes the APU starter generator, and starts the 60-second timer for the cooldown period. The cooldown period preserves the life of the APU hot section and prevents coke from accumulating in the turbine bearing and fuel nozzles. As the APU speed decreases below 30%, the APU fuel shutoff valve and inlet door start to close. If the APU fuel shutoff valve does not close, the fault light will illuminate after approximately 30 seconds. Below 7% RPM, an APU restart can be initiated if desired by moving the APU switch back to start. The APU can be shut down immediately without the 60-second cooldown period by pulling the APU fire switch. Clearly, this is not standard practice and should only be done in an emergency. Under certain conditions, the APU will shut down automatically to prevent damage to itself or other aircraft components. This is called a protective shutdown. There are 3 different indications in the cockpit that indicate a protective shutdown, and all 3 are on the APU panel. The low oil pressure light illuminates when oil pressure drops below limits for 20 seconds or more. This causes a protective shutdown. The fault light illuminates for a large number of conditions. The fuel shutoff valve not in the commanded position. The inlet door not in the commanded position. Loss of DC power. Electronic control unit failure. APU fire. APU inlet overheat. Loss of both EGT signals. No APU speed signal. No APU deceleration. No APU rotation. Low EGT after introduction of fuel, the generator filter being clogged, high oil temperature, APU over temperature, reverse flow through the load compressor, oil temperature sensor failure, inlet temperature sensor failure, and APU under speed. Any one of these will trigger a protective shutdown. Finally, the overspeed light will illuminate for a further 3 conditions. If the fuel control unit solenoid valve fails in the open position, a loss of overspeed protection, and APU overspeed. Any one of these will trigger a protective shutdown. The low oil pressure, fault, and overspeed lights will extinguish when the APU switch is cycled to off, then back on again with APU speed less than 7%. Why 7%? Because that's the speed below which the APU can be restarted again. The maintenance light illuminates when oil pressure drops below a specified level, or if the starter generator has a shorted rotating diode. In both cases, the APU may continue to run, but will require maintenance as soon as possible. Any one of the individual conditions we listed could be discussed at considerable length, but are rather beyond the scope of what we need to cover in this lesson. The key thing to realize is that there is a considerable amount of protection against conditions which might damage the APU or other aircraft components. We'll finish up here with a lesson summary. Although the APU on the next generation 737 is around 12 decibels quieter than that on the classics, airports are increasingly cracking down on APU use to reduce noise levels on the ramp. It is also far more efficient to make use of ground power where available, as this does not consume fuel. In many cases, however, the self-sustainability that the APU provides is invaluable and is a vital part of the aircraft's power system. In this lesson, we covered an overview of the auxiliary power unit and its primary components, APU fuel supply, the start sequence, operational modes, altitude operational limits, shutdown, and automatic load shedding.